Hello everyone, this is Dr. Sandeep Kumar, Assistant Professor, Ramjas College, University of Delhi. So in the last few lectures, we have started the lecture series on heterocyclic compounds. And till now, we have discussed that heterocyclic compounds are the compounds which contain heteroatom other than carbon atom as well. And thereafter, we have discussed the biological importance of heterocyclic compounds. Then we discussed classification of heterocyclic compounds, and thereafter we discussed about the nomenclature of heterocyclic compound. And then we started with individual heterocyclic compounds. So in the series, first we discussed about pyrrole compound. So pyrrole is a 5-member heterocyclic compound with nitrogen as heteroatom. In pyrrole, we discussed about the different method for the synthesis of pyrrole compound. Then we discussed about the structure of pyrrole, then its physical properties and chemical properties. Thereafter, in the last lecture, we started with furan compounds. In furan compound, we follow the same pattern that in the first of all, we discussed synthesis of furan by using different methods. Then we discussed structure of furan and its physical and chemical properties. In the chemical properties, we discussed about halogenation, nitration, sulfonation, acylation reaction, alkylation reaction, Willsmere-Hack reaction, and basic character of furan. So in this lecture, we are continuing the chemical properties of furan compound. So the next chemical reaction of furan molecule is that it will undergo the ring cleavage when we use acidic condition. So under controlled condition, furan and its derivative can undergo ring opening reaction in acidic medium to yield 1,4-dicarbonyl compounds or their derivatives. As you can see, in the first example, we have taken 2,5-dimethyl-furan as the compound, and on treatment with aqueous sulfuric acid, it will produce hexane 2,5-dione as the product. And in the second example, we have taken furan molecule itself, and when it undergo treatment with hydrochloric acid in methanol, then it will produce succinaldehyde methyl acetal as the final product. The next reaction of furan is reduction of furan. So reduction of furan can be carried out by using hydrogenation condition. So in the hydrogenation, we use hydrogen on Raney nickel, and the final product will be tetrahydrofuran. So, and we know very well about the tetrahydrofuran, which is a valuable solvent that is commonly used in many organic syntheses. And one of the example is that it is used in the preparation of Grignard reagent. The next reaction of the furan is oxidation of furan. So unlike pyrrole, furan react with oxygen to form first of all a 1,4-peroxide molecule, this molecule, and which upon further oxidation produce succinaldehyde as the final product. Then the next reaction of furan is cycloaddition reaction. So this is one of the most beautiful reaction of furan, because furan behave as aromatic compound as well as it behave as diene-like system. So because of two double bonds in conjugation, it behave like 1,3 butadiene system. So when we have this diene system and we have dienophile like malic anhydride, so there will be 4+2 cycloaddition reaction between these two components, and it will produce the Diels-Alder product as the final product. And in similar way, when there is dienophile as benzene, then there also there will be 4+2 cycloaddition reaction between furan and benzene, and once again there will be formation of Diels-Alder adduct as the final product. The last reaction about furan molecule is once again from the nature of diene-like character. So furan react with carbenes through a cycloaddition reaction to produce cyclopropane derivative. And the example is that the reaction of furan with diazomethane in the presence of copper bromide produce cyclopropane fused furan adduct. So we have furan molecule and there is diazomethane. In presence of copper bromide, it is producing cyclopropane fused furan molecule. So in this reaction, first of all, there will be formation of carbene by reaction between diazomethane and copper bromide. So and that carbene will react with furan in a manner of cycloaddition reaction, and there will be formation of cyclopropane fused furan as the final product with the elimination of nitrogen. Now we are going to start with the third compound in the lecture series, that is thiophene molecule. So in thiophene we will discuss the introduction of thiophene, then we will discuss the structure of thiophene molecule, thereafter physical properties of thiophene, and then we will discuss the different synthetic method used for the synthesis of thiophene molecule. The first method will be the synthesis of thiophene from sodium succinate, thereafter synthesis from acetylene, then synthesis from hydrocarbons, and then we will discuss two name reaction. First will be Paulnor synthesis and the second will be Hinsberg synthesis. So after the synthesis part, we will discuss the chemical properties of thiophene molecule, and in the chemical properties the reaction will be electrophilic substitution reaction, and in electrophilic substitution reaction we will discuss different kind of electrophilic substitution reaction. The first will be halogenation reaction, thereafter nitration, then sulfonation, alkylation reaction, then we will discuss the reduction of thiophene by using different condition for the reduction, and at the last we will discuss the reaction of thiophene with carbenes. So let's start with the basic introduction of thiophene molecule. So as you can see, thiophene is a 5-member heterocyclic compound that contains a sulfur atom. It naturally occurs in the light oil fraction of coal tar and is commonly found as an impurity in commercially available benzene. And you can see the position assigned to thiophene molecule. So after the heteroatom, the first carbon is named as first 1, then 2, 3 and 4, and we can also assign the numbering of carbon by using alpha position and beta position. So now we are going to discuss the structure and aromatic character of thiophene molecule. So the molecular formula of thiophene was found C4H4S, and based on the carbon's tetravalency and sulfur's valency, thiophene initially be represented as diene-like character. So you can see in this structure that the yellow part of this molecule represent a diene-like system, and in this system all the carbon atoms and sulfur atoms are sp2 hybrid. So, now we are going to prove that this molecule is an aromatic in nature. So, for that we have to consider the electronic configuration of atoms in this molecule, and the atoms are carbon and sulfur. So, the electronic configuration of carbon atom in the excited state will be like that. There will be one electron in the 2s orbital and one electron in 2px orbital, one electron in 2py orbital and one electron in 2pz orbital. In similar way, we are considering the electronic configuration of sulfur atom in the excited state. So, there will be 2 electrons in the 3s orbital and 1 electron in 3px orbital, 1 electron in 3py orbital and 2 electrons in 3pz orbital. And as I told you that both carbon and sulfur are sp2 hybrid, then the hybridization of carbon and sulfur will be like that. There will be contribution of s orbital and 2p orbital in each carbon and sulfur atom. So, each carbon atom has one electron in each of its 3 sp2 hybrid orbital and one electron in an unhybrid p orbital. In similar way, sulfur atom has 3 sp2 hybrid orbital, two of which contain one electron each, while the third hold a lone pair of electrons. Additionally, sulfur has an unhybrid p orbital that contains another lone pair of electrons. You can see in this slide that there are 3 sp2 hybrid orbital, and this orbital of carbon is unhybrid, which do not participate in the bonding. In similar way, in sulfur atom, these 3 are sp2 hybrid orbital, and this last 3pz orbital is unhybrid p orbital. So, now we are going to discuss how these hybrid and unhybrid orbitals are utilized by carbon and sulfur atom. So, carbon atoms utilize their sp2 orbital to form 3 sigma bonds. The first sigma bond will be between carbon-carbon, the second will be between carbon-hydrogen, and the third will be between carbon-sulfur. So, while sulfur use of its sp2 orbital to form 2 sigma bond, that will be carbon-sulfur bond, and the third sp2 orbital of sulfur which hold a lone pair of electrons lies in the plane of the ring, which does not participate in pi bonding, and it remains as non-bonding pair of electrons. So, the unhybrid p orbital of 4 carbon atoms and which contains 1 electron each. You can see in this structure that each carbon atom has unhybrid p orbital which contain 1 electron, and there is sulfur atom which also contain unhybrid p orbital, and that p orbital contains a pair of electrons. So, these 6 electrons will do sideway overlapping to form a 6 pi electron system. 6 pi electron system like be 4 electrons from each carbon and 2 electrons from the sulfur atom. So, there will be formation of a 6 pi electron system by the sideway overlapping of p orbital, unhybrid p orbital. And because we know that any system which has 6 pi electrons will follow Huckel's 4n plus 2 pi electron rule and will be considered as aromatic system. So, hence we proved that thiophene is an aromatic compound. So now we are going to discuss the physical properties of thiophene. So the first thing about thiophene is that thiophene is a colorless liquid. It has boiling point around 357 Kelvin. The smell of thiophene is very similar to that of benzene, and it is insoluble in water but soluble in most of the organic solvents. Now we are going to discuss the synthesis of thiophene molecule by using different methods, and these different methods will be the synthesis from sodium succinate, synthesis from acetylene molecule, and from hydrocarbons, Paul-Knorr synthesis, and the last will be Hinsberg synthesis. So let's start with the synthesis of thiophene molecule from sodium succinate. So thiophene can be prepared by heating sodium succinate with phosphorus trisulfide, and the synthesis is very common and usually carried out in the laboratory. So this molecule is sodium succinate, and in the presence of phosphorus trisulfide on heating, it will produce thiophene in almost quantitative yield. The next synthesis of thiophene will be from acetylene molecule. So thiophene can be prepared by passing a mixture of acetylene and hydrogen sulfide over alumina at 6073 Kelvin, and the synthesis is also adopted by at commercial level. So in this synthesis, two molecules of acetylene react with hydrogen sulfide in the presence of alumina at a very high temperature. The temperature should be above 600 Kelvin. So we will get thiophene as the final product with the elimination of hydrogen from the reaction mixture, and this hydrogen can be utilized for different purposes. The next synthesis of thiophene molecule is that it can be synthesized from hydrocarbons. So thiophene is also industrially synthesized by reacting N-butane with sulfur in the vapor phase. Means we need very high temperature. The temperature should be around 833 Kelvin, and when we react N-butane with excess amount of sulfur, then we will get thiophene as the final product with the elimination of hydrogen sulfide. And if we want to synthesize the derivative of thiophene molecule, then we can take different isomers of hydrocarbons. For example, if we take isoprene as the reactant system, then in presence of sulfur, it will produce 3-methyl thiophene as the final product with the elimination of hydrogen sulfide. The next synthesis of thiophene is Paul-Knorr synthesis. The synthesis is very famous, and the same synthesis can be carried out for the synthesis of pyrrole and furan molecule. So this is a general method for synthesizing thiophene derivatives, which involve heating an enolizable 1,4-diketone with phosphorus trisulfide or phosphorus pentasulfide. For example, we have hexane 2,5-dione as the organic compound, which is kind of 1,4-diketone system, because in this molecule both the keto groups are separated by 1,4 position. That's why we are calling it 1,4-diketo compounds. So this compound on reaction with phosphorus trisulfide, or we can take phosphorus pentasulfide, then we get 2,5-dimethyl thiophene as the final product. Let me discuss the mechanism of this reaction. In this reaction, the starting diketone is first converted into a thioketone molecule using sulfurizing agent. This sulfurizing agent can be phosphorus trisulfide, phosphorus pentasulfide, or we can use Lawson's reagent for the sulfurization. And these sulfurizing agent will also do the dehydration in the final step as well. So, suppose we have hexane 2,5-dione as the reactant system, and in presence of sulfurizing agent there will be formation of thioketone intermediate. Then this thioketone intermediate will be tautomerized into enol form, and then there will be intramolecular nucleophilic addition reaction on the electrophilic carbon of this carbonyl group by the sulfur atom. So, after nucleophilic addition we will get this intermediate, and from this intermediate there will be dehydration take place to get the final product, that will be 2,5-dimethyl thiophene. The last synthesis of thiophene molecule is the Hinsberg synthesis. So, in this synthesis, the condensation of a 1,2-dicarbonyl compound like benzyl, this compound, with diethyl thiodiacetate in the presence of base like sodium ethoxide will be carried out in ethanol, and followed by acidic hydrolysis yield the thiophene derivative. So, we have benzyl, that is kind of 1,2-dicarbonyl compound, and we have diethyl thiodiacetate. So, in presence of base, that is sodium ethoxide, it will produce thiophene derivative as the product. So, the mechanism can be understood. We have two components, one is benzyl and the second is diethyl thiodiacetate. So, the acidic proton of diethyl thiodiacetate will be abstracted by the base, and there will be formation of carbanion, and this carbanion will attack on the electrophilic carbon of this benzyl, and there will be formation of this intermediate. Then in this intermediate there will be nucleophilic addition followed by elimination reaction. So, nucleophilic addition will take place on the electrophilic carbon of carbonyl group, and there will be elimination of ethoxide ion to form a cyclic intermediate. Then in the presence of base there will be abstraction of alpha hydrogen, and there will be ring opening reaction. So, after the ring opening we will get this intermediate, and further in presence of base, that is sodium ethoxide, there will be abstraction of alpha hydrogen, that is acidic in nature, and after the abstraction there will be formation of carbanion intermediate, and this carbanion will do intramolecular nucleophilic attack on the electrophilic carbon of carbonyl compound, and after intramolecular attack there will be formation of a 5-member ring with sulfur as the heteroatom, and from this intermediate there will be elimination of water molecule, and we will get thiophene derivative, and further the hydrolysis of ester into acid will be carried out by using acidic aqueous medium. So, in this way we can synthesize different thiophene derivative by using Hinsberg method. Now, we are going to discuss the chemical properties of thiophene molecule. So, thiophene, very similar to furan and pyrrole, exhibit aromatic character. We have just proved that thiophene is an aromatic compound. So, therefore, it will show the characteristic reaction of aromatic compounds, and those characteristic reactions are electrophilic substitution reactions. But the problem is that among the 3 5-member heterocyclic compound, it is the least reactive. Unlike pyrrole, it does not display basic properties and is significantly more resistant to acid than both pyrrole and furan. So, the electrophilic substitution reaction in thiophene will be on the same position as was in pyrrole and furan compound. So, the position will be second position, that will kind of alpha position of thiophene molecule. So, in electrophilic substitution, we will discuss the different kind of electrophilic substitution reaction like nitration, sulfonation, acylation reaction, Willsmere-Hack reaction, then mercuration reaction. So, one by one, let us start with halogenation reaction of thiophene molecule. So, thiophene undergo halogenation very quite easily even at low temperature around 30 degrees Celsius or at room temperature. In fact, its halogenation at 25 degrees Celsius is about 10 to the power 8 times faster than that of benzene molecule. And the chlorination of thiophene can be carried out by using different conditions, like we can use chlorine molecule, we can use thionyl chloride, and we can use N-chlorosuccinamide. And in different conditions, we will get the different product. Like you can see in this slide, that when we have thiophene and we want to do chlorination with chlorine molecule, then it will produce a mixture of product. The mixture of products will contain 2-chlorothiophene, 2,5-dichlorothiophene, 2,4,5-trichlorothiophene, and 2,3,4,5-tetrachlorothiophene. And when we use tin chloride in lead acetate, then we will get 2,5-dichlorothiophene as the only product. And by using N-chlorosuccinamide, we get only single product, that will be 2-chlorothiophene. So, the next course will be discussed in the next lecture of the series. Thank you very much.